Have you ever wondered what it would feel like to stand at the edge of the solar system and watch a stranger from the stars drift in? Imagine, far out there, beyond Mars, a visitor, a body of ice and dust moving through our neighborhood at unimaginable speed. The sun twists and writhes, its magnetic field snapping like ropes under tension, hurling out colossal storms of plasma, and yet this interstellar traveler sails through, untouched. 3 coronal mass ejections in its path, 3 violent waves of energy and magnetism, and somehow it just keeps going. Why? How can a fragile object, smaller than a mountain, almost ignore the fury of our star? What are we missing in the way we think about solar wind, or momentum, or the very nature of magnetic space? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Tell me, where are you on the map tonight? Are you somewhere under northern lights? Or perhaps in a city where the sky never quite goes dark? It's always fascinating to see who's joining us from all around the world. So let's continue, because tonight we'll unfold this mystery layer by layer, what we've seen, what physics predicts, and what's still open to debate. And, maybe by the end, you'll find that the real story isn't just about a comet or a CME, it's about how fragile things endure, even in the heart of chaos. You see, when we talk about a journey through the solar system, we often imagine graceful arcs and elegant ellipses, paths bound by the sun's pull, each orbit a dance of gravity and light. But our interstellar visitor, the one we call 3I Atlas, does not dance in circles. It comes and goes like a whisper cutting through the noise, following a path so open, so unrestrained, that it defies the very idea of being bound. Its trajectory is not an orbit at all, but a hyperbola, a curve of escape, a reminder that not all who pass near the sun are held by it. A hyperbolic orbit, well, it's a strange thing. If you were to trace it on a sheet of paper, it would look like 2 arms reaching out forever, never closing. The shape itself tells us something fundamental. The object's eccentricity, the measure of how stretched its path is greater than 1. That number alone whispers that it will never return. It comes once, from the deep dark between the stars, and once it leaves, it will never be seen again. Its speed, even at infinity, what astronomers call the velocity at infinity, remains greater than 0. In other words, no matter how far it travels, no invisible hand will slow it to a stop. Imagine standing near the sun, if such a thing were possible. You watch as this small, icy fragment sweeps past, and the immense gravity of our star tries to bend its path. The sun tugs at it, distorts the trajectory ever so slightly, but only slightly. The visitor doesn't spiral inward or linger. It merely bows in respect, then glides away. It's a bit like skipping a stone across the surface of a pond. The water may ripple, but the stone never sinks. It's gone before you can even count to 3. And that's the thing about hyperbolic motion. It reveals not just the nature of the traveler, but also the subtle balance between speed and gravity. The faster an object moves, the shallower the bend of its path. If the sun's gravity is a hand trying to hold it, then the object's momentum is the refusal to be held. This delicate contest plays out in silence, through the void, governed by equations older than any language we speak. You might even say that the orbit is a kind of conversation between matter and motion, between what wants to stay and what must go. Now, 3I Atlas didn't just happen to wander into this gravitational stage by accident. Its path was mapped with extraordinary precision by observatories on Earth and spacecraft peering from orbit. Each night, astronomers measured its position against the background of stars, plotting tiny points of light, building what's called an ephemeris, a prediction of where it would be next. And the predictions held, almost eerily well. Even as solar flares erupted and the sun released waves of charged particles, 3I Atlas stayed on track. Its motion through space was as calm and predictable as a stone through air. But how do we know such things, really? When we say its orbit was hyperbolic, that its eccentricity was greater than 1, we're not describing something we can see directly. We infer it through the Doppler shift of light, through astrometry, through the slow drift of pixels across a sensor. It's almost poetic in a way. The knowledge of its freedom comes not from watching it leave, but from listening to the faint shift in its song of light. And this song tells us even more. You see, the speed of 3I Atlas as it approached the inner solar system was tremendous. By the time it neared the orbit of Mars, it was moving at tens of kilometers per second, fast enough that even the sun's immense gravity could only bend its path by a few degrees. Think about that. The same gravity that holds Earth in a billion-year embrace could not detain this small, icy fragment for more than a moment. It's humbling, isn't it? That something so small can move so fast, and yet so surely. If we think of the solar system as a well, a deep gravitational pit, with the sun at its center, then planets like Earth are pebbles resting along the inner slopes, rolling gently around the curve, held by gravity's pull. A hyperbolic object, on the other hand, is like a cometary seed flung from a distant field, skimming the edge of the well, too fast to fall in. It glances past and escapes, carrying stories from places we may never reach. Astronomers use another term for this: escape velocity. It's the speed you must reach to break free from a celestial body's grip. For Earth, it's about 11 kilometers per second. For the Sun, at the distance of Earth, it's roughly 42 kilometers per second. Our visitor exceeded that easily. It didn't just escape, it was never bound in the first place. That single fact changes everything. It means that 3I Atlas was born elsewhere, beyond the influence of our star, beyond even the Oort cloud that fringes the outer solar system. It came from the deep interstellar medium, carrying within it the chemistry and history of another sun. But there's something even more intriguing here. For an object to travel through our solar system and maintain a hyperbolic trajectory so clean, so unperturbed, it must have passed through the gravitational fields of planets, solar wind, and even coronal mass ejections without significant deviation. Statistically, that's rare. The solar system is vast, yes, but it's not empty. To pass through 3 solar events, each capable of twisting magnetic fields and pushing streams of charged particles, and still maintain a mathematically perfect orbit, well, that's remarkable. It's as if it slipped through the spaces between chaos. Perhaps this is why so many astronomers found themselves staring at the data, wondering if something had been missed. Could its mass be larger than estimated? Could it be denser or its shape more aerodynamic? Or perhaps, was there something about its material composition that allowed it to resist the drag of solar wind more efficiently than a typical comet? These are not idle questions. They touch on the very way we understand motion through magnetized plasma, the way matter and field converse in the silence of space. I often find myself thinking about how these paths, these silent arcs of dust and ice, are like threads woven through the sun's invisible web. Each orbit, each trajectory, is a line drawn through space-time, and when we follow it, we trace not only the motion of the object, but the shape of the solar system itself. A hyperbolic orbit is like a fleeting sketch of the sun's gravitational face, seen only once, then lost forever. And so we return to the heart of the mystery. If 3I Atlas's path was indeed so clean, so true to the models, why did the sun's violent outbursts seem to have no effect? Was it a matter of geometry, that the solar storms missed its core, brushing only the edges of its faint atmosphere? Was its nucleus shielded by a coma dense enough to absorb the shock without altering the center of mass? Or could it be that the forces we calculate, the drag from ionized particles, the electromagnetic coupling between coma and wind, are weaker than we think at these scales? These questions hover, unanswered, suspended like dust in sunlight. The hyperbolic path gives us the framework, the mathematics, but not the meaning. The meaning, perhaps, lies in how nature finds balance between motion and resistance, between the order of equations and the unpredictability of plasma. And as we trace that balance, we begin to see how the journey of 3I Atlas tells a larger story, one that stretches from pure geometry to the living dynamics of the sun itself. Because while Chapter 1 belongs to motion, to the quiet certainty of trajectories and numbers, the next will belong to what our eyes cannot see, the hidden breath of the comet, the mist of gases and dust that reveal its invisible conversation with sunlight and magnetism. So let's step a little closer now, into the light itself, into the shimmering veil that's SU. When 3I Atlas drew closer to the inner solar system, something subtle began to change. From a distant point of light, steady and indifferent, it transformed into something alive, a body surrounded by a halo of mist, as if it were exhaling after an eternity of silence. The sun's warmth, even across millions of kilometers, began to stir the frozen layers of its surface. Molecules that had been locked in darkness since before our planet formed began to vibrate, to drift free, and to form a delicate envelope of gas and dust. Astronomers call it the coma, though the word itself hardly does justice to its fragile beauty. To the eye, it is a ghostly sphere surrounding the nucleus, an atmosphere without a planet, a breath without lungs. You might imagine it as a kind of twilight shell, faint but luminous, stretching tens of thousands of kilometers. Within it, grains of dust float and scatter sunlight, creating that soft cotton-like glow that makes comets appear almost alive. It's easy to forget that at the center of this faint sphere lies a solid heart, only a few kilometers across, a relic of another system, carrying within it the fingerprints of a different star. But the coma is more than decoration. It is a map of physical processes. Each shimmer, each tendril of light, speaks of temperature, radiation, and chemistry at play in real time. And the coma, you see, is the beginning of everything that follows the birthplace of the tails that stretch out like ribbons across space. Now, when the sun's photons strike this newly awakened atmosphere, two things happen. The light itself pushes ever so gently on the dust grains that drift in the coma. This pressure, though faint, acts over vast distances, nudging the particles away from the sunday. The result is what we call the dust tail, a sweeping, curved arc that trails behind the comet's motion. It is not perfectly straight. It bends, like smoke caught in a slow wind, following the comet's orbital path, but always leaning away from the star. The color of this tail is soft and warm, golden, because it reflects sunlight rather than emitting its own. In the case of 3I Atlas, high-resolution images revealed that the dust tail was composed of fine particles, likely smaller than a grain of sand, streaming away in smooth gradients, rather than clumps. That tells us something intimate about its nature, that it was shedding material gently, not through explosive jets, but through quiet sublimation, the patient breathing of ancient ice. But there is another tail, and this one belongs not to dust, but to ions. When the sun's radiation encounters molecules in the coma water, carbon dioxide, carbon monoxide, it tears them apart, stripping electrons and leaving charged fragments. These ions are immediately caught by the solar wind, a stream of charged particles flowing outward from the sun at hundreds of kilometers per second. The magnetic field embedded within that wind sweeps through the comet, and the ions, like iron filings in a magnetic current, are forced to align along its lines of force. The result is a second tail, the ion tail, stretching straight away from the sun, often glowing in shades of electric blue. It is thin, sharp, and restless. While the dust tail curves gracefully, the ion tail flickers and bends with every gust of solar wind, a living needle of plasma, tracing the magnetic breath of the sunday. In the case of 3I Atlas, these two tails overlapped beautifully, a soft, golden plume of dust, veiling a sharp azure line of ions, the two intersecting at a subtle angle. Astronomers could see this geometry even from Earth, mapping the way sunlight and solar wind sculpted the material. Each tail told a different story, one of matter, the other of energy. One born of reflection, the other of reaction. And in this duality, there was a glimpse of how stars shape everything around them. The comet wasn't simply passing through the sun's domain, it was participating in it, exchanging energy and matter in the smallest yet most profound of ways. What fascinates me most, perhaps, is that the structure of the coma and tails can tell us about what the nucleus is made of. Certain gases, carbon monoxide, carbon dioxide, methane sublimate at different temperatures, Comet's coma contains more carbon dioxide than water vapor. It may suggest that it formed in a colder, more distant region of its original system. When astronomers took spectroscopic measurements of 3I Atlas, they found signatures that hinted at something unusual, an excess of carbon-bearing molecules, with relatively little water. That might mean it was born in the outer reaches of another star's protoplanetary disk, where temperatures were so low that even carbon dioxide could freeze. And so, hidden in those faint blue and white wisps was a story billions of years old, carried across the void, now illuminated for the first time by our Sunday. The interplay between the coma and the tails is also a story of delicate forces. The sun's radiation pressure, though it seems weak, exerts a measurable influence on the dust particles. Larger grains, being heavier, move slowly and form the curved path of the dust tail, while smaller grains, lighter and more easily pushed, drift outward faster. The ion tail, on the other hand, has almost no mass at all in human terms, but responds instantly to changes in the solar wind. When a coronal mass ejection passes through, the ion tail can bend or even detach entirely, forming bright kinks or sudden disconnections that reveal the invisible turbulence of space weather. To watch a comet's tail shift in this way is to see the sun's heartbeat played out in matter and light. For 3I Atlas, this dance was particularly instructive. Despite the solar activity it encountered, the core trajectory remained stable, but the coma and tails served as living sensors of those interactions. At times, the ion tail brightened abruptly, as if struck by a pulse from the Sunday. Then, just as suddenly, it would fade, and the dust tail would regain its serene arc. It was almost as though the comet were absorbing the storm, redistributing its energy, and continuing its journey undisturbed. Perhaps this is part of the reason the main body did not deviate. The energy of the impacts was dissipated within the vast, diffuse cloud of gas and dust, leaving the nucleus untouched. The coma may have acted as a shield, an invisible buffer between the solar wind and the solid core, smoothing out the violence of cosmic weather. If you imagine the scene in 3 dimensions, the effect is extraordinary. The nucleus, a dark pebble wrapped in a cocoon of light, drifts along a vast, invisible river of magnetism. Behind it, 2 luminous banners flow outward, one graceful and curved, the other taut and straight, both sculpted by forces we can only measure indirectly. And the whole system, though millions of kilometers across, is governed by laws that can be written on a single page: Newton's gravitation, radiation pressure, ionization, magnetohydrodynamics. Yet the result, when seen through a telescope, feels almost emotional. It is as if nature, for a fleeting moment, has chosen to paint with light. The scientists who studied 3I Atlas during its passage found themselves revisiting old assumptions about what happens when interstellar comets interact with our star. Many had expected violent jets or irregular behavior, as sublimation unleashed chaotic forces. Instead, what they saw was balance, a kind of calm resilience. The comet adjusted, responded, and continued. Perhaps this is the most surprising lesson, that even amid the sun's storms, there exists a quiet equilibrium, a conversation between radiation and matter that finds its own harmony. And so, as the coma expanded and the tails lengthened, 3I Atlas revealed itself as more than a mere traveler. It became a witness to the physics of our star, a mirror reflecting its energy in real time. Each image captured by Earth's telescopes was a fragment of that dialogue: sunlight scattered, ions torn and guided, molecules fleeing the surface and forming clouds in the vacuum. The more we watched, the more it seemed as though the comet was teaching us about our own sun, showing us how its breath extends far beyond its visible edge, shaping everything that dares to approach. It's strange, isn't it, how something so small can act as a laboratory for forces so vast. A few kilometers of ancient ice, carrying dust from another system, can reveal the texture of space between worlds. And every comet, every traveler like 3I Atlas, reminds us that the solar system is not a closed chamber, but an open stage where the universe comes and goes, leaving traces of its long journeys. The coma fades as distance grows. The tails stretch out, disperse, and are lost in the glare of the Sunday. But the data remains the spectral fingerprints, the brightness curves, the subtle polarization of scattered light. These are the clues that allow us to reconstruct what we cannot touch, to turn a faint blur in the sky into a detailed story of physics and time. And as we follow these traces, we begin to wonder what lies beneath the visible, what hidden structures or forces might shape the way 3I Atlas moves, breathes, and endures. Because beneath that luminous veil, behind the haze of dust and the whisper of gas, lies something darker and harder to see: the true nucleus, the solid heart from which all this beauty emanates. A body ancient, compact, and mysterious, whose surface tells of impacts, heat, and long ages in the dark between stars. To understand the coma fully, we must descend to that core, to the hidden engine of sublimation, and the secret of how such a small object commands so grand a presence. And so, as we drift inward, leaving the glowing atmosphere behind, we turn our gaze toward the heart of 3I Atlas itself, where the story of its origins, and perhaps its endurance, begins to unfold. When we peer beneath the luminous veil of 3I Atlas, past the soft glow of its coma and the flowing tails that stream outward into the dark, we arrive at the heart of the mystery, the nucleus itself. It is a place that no human eye has seen directly, a body smaller than many mountains, black as volcanic glass, spinning slowly as it travels through sunlight. Everything we know of it comes not from what we see, but from what its light tells us. For astronomers, this is where the art of spectroscopy begins, a way to listen to the light, to translate photons into chemistry, and in doing so, to trace the story of an object born under another sun. High-resolution imaging played the first role in this inquiry. When the coma of 3I Atlas began to expand, telescopes on Earth and in orbit turned toward it, capturing frames in multiple wavelengths, from visible to infrared. Each pixel carried within it faint clues, a flicker in brightness, a gradient in color, a shift in albedo. From these subtleties, scientists could infer the approximate size of the nucleus, estimating that it was only a few kilometers across. But brightness alone can be deceptive. A darker surface, one coated in complex carbon compounds, can reflect very little sunlight, making a large body appear small. Conversely, a more reflective one can seem deceptively large. To separate these effects, astronomers relied on the interplay of light and heat, how much the object shone in visible light compared to how much infrared radiation it emitted as warmth. By combining these data, they could constrain its albedo and surface composition, like a sculptor feeling out the shape of a statue through cloth. As the comet brightened and faded, its spectrum began to reveal the fingerprints of its materials. The lines and bands in that spectrum, narrow features where light was absorbed or emitted, told of molecules set free from the surface. Water vapor, carbon dioxide, and carbon monoxide were among the first to appear, but their relative strengths painted a curious picture. On Earth, and in the comets of our own system, water vapor usually dominates. It is the signature of ice responding to sunlight. But in the case of 3I Atlas, the balance seemed different. Carbon dioxide appeared more strongly than expected, while water's signal was faint, almost hesitant. That alone suggested a world of colder birth, a nucleus formed so far from its native star that carbon dioxide, which would normally evaporate early, could condense into ice and remain frozen for billions of years. You can think of a spectrum as a kind of coded story. Every line is a word, every cluster of lines, a sentence. When astronomers look at these spectral fingerprints, they are reading an ancient script written in light. The presence of carbon monoxide, for instance, tells of extreme cold. Methane or ammonia would hint at even more distant, shadowed regions. Each molecule carries not just chemical information, but a memory of environment, the pressure, temperature, and radiation of the cloud in which the comet was born. And because 3I Atlas came from another stellar nursery, its pattern of lines acts like a sample from a different universe of chemistry, a snapshot of how other planetary systems assemble themselves from dust and gas. From a more technical point of view, The way we measure these lines is astonishingly delicate. A single spectral observation often involves spreading the light of the comet across a detector until the faintest details emerge. The instrument records how much energy arrives at each wavelength, building a profile that scientists then compare against laboratory spectra of known molecules. In the data from 3I Atlas, subtle absorption features corresponded to diatomic carbon and cyanogen, both common in comets yet powerful indicators of active photochemistry. When sunlight strikes these molecules, they glow faintly in blue and green, giving the coma its characteristic hue. So, even the color of the comet, as seen through a simple telescope, is the visible consequence of molecular physics, a dance of electrons excited by the touch of solar photons. But spectroscopy does more than list ingredients. It tells of motion. By measuring how those spectral lines shift slightly toward red or blue, scientists can calculate how fast gas is escaping from the nucleus, and in what direction. For 3I Atlas, the data suggested that jets of gas streamed outward at several hundred meters per second, forming uneven patches within the coma. These outflows can spin the nucleus, altering its rotation over time. The rhythm of brightness variations, periodic fluctuations seen in long observation, runs hinted at a rotation period of several hours, perhaps a day, though no one could be certain. Each flicker represented sunlight glancing off ridges, hollows, and slopes on the irregular surface of that tiny interstellar body. And there's something poetic in that, don't you think? To know the turning of a rock from another star by watching it shimmer through a sea of light years. To imagine that on its surface, frozen plains crack and vent, releasing jets that carry whispers of alien chemistry into the vastness. The light that reaches our telescopes is already centuries old, in a sense shaped by atoms that were born in long-dead stars, carried into a new one, and now scattered again into space. As 3I Atlas approached perihelion, the point in its path nearest to the Sun, its brightness increased dramatically. Observatories from Hawaii to Chile, from space telescopes to backyard instruments, followed it nightly, mapping the spectral changes as the heat grew more intense. The abundance of volatile gases shifted, some lines strengthened, others faded. In the ultraviolet, emissions from ionized carbon and oxygen flared, signatures of molecules broken apart by solar radiation. These changing spectra acted like a weather report for a world that had never known seasons, the frozen chemistry of interstellar space, now responding to sunlight for the first time in perhaps billions of years. One of the most fascinating results came from comparing 3I Atlas with known comets of our system. Its spectral fingerprints matched none of them precisely. Some ratios of molecules resembled those seen in long-period comets from our Oort cloud, while others were closer to what we'd expect in objects from colder, younger disks. It was as if 3I Atlas carried elements of both a hybrid chemistry that hinted at diversity among planetary systems. Maybe, somewhere out there, around a distant star, a disk of dust and ice gave birth to comets richer in carbon than ours, less shaped by water, more tempered by darkness. And one of them, by some ancient gravitational nudge, was sent wandering across interstellar space until, by pure chance, it found its way here. The shape and brightness of its coma also provided indirect clues about the size and albedo of the nucleus. By modeling how sunlight scattered through the dust and how that dust thinned with distance, scientists could estimate how much material was being released per second. It's a kind of inverse reasoning. If you know how bright the fog is, you can estimate how much fog there must be, and therefore how strong the source is beneath it. For 3I Atlas, the estimated production rates placed it somewhere between modest and surprisingly active for its size, suggesting either a higher fraction of volatile ices or a surface unusually efficient at absorbing heat. Both ideas add nuance to our understanding of interstellar bodies, which may vary in ways our own comets do not. Infrared observations from space-based instruments revealed more. The heat signature of the dust suggested that particles in the coma were fine and carbon-rich, absorbing sunlight efficiently and re-radiating it at longer wavelengths. Such material would contribute to the comet's dark surface, consistent with the low albedo inferred earlier. Carbon-rich coatings are common in ancient comets, but the ratio measured for 3I Atlas was extreme, a surface almost black, reflecting perhaps only a few % of incoming light. That could explain its subtle glow, even at high activity. Most of the sunlight was being absorbed, not reflected, fueling sublimation rather than brilliance. And that darkness, that quiet invisibility, may have shielded it from the sun's most violent flares, distributing heat more evenly across its surface and preventing localized cracking or fragmentation. There's an elegance in how all these details, brightness, spectrum, polarization, converge into one story. They tell of a nucleus both familiar and foreign, a piece of solid matter that obeys the same physics but carries a different history. The more we looked, the clearer it became that this wasn't merely another comet passing through. It was a messenger from a place where chemistry and time followed a slightly different path, a sample of the wider galaxy delivered into the reach of our instruments. And yet, for all we learned through light, there remained a question: could we truly trust the patterns we saw? The coma, after all, acts as both a lens and a veil. It scatters, absorbs, and re-emits light in ways that complicate our measurements. Disentangling those effects requires models, simulations that account for dust size, gas flow, radiation pressure, and geometry. In the case of 3I Atlas, those models often produced results within error, but never perfectly consistent. It was as if some small influence was missing, something unaccounted for in the simple equations of outgassing and reflection. That tiny discrepancy would become important later, when we considered how 3I Atlas managed to maintain such a stable trajectory through solar events that should have nudged it. Sometimes, in science, the answers hide not in what fits, but in what does not. Still, the spectra told us enough to paint the nucleus in our minds. Picture it, a lumpy, irregular shape, perhaps 3 or 4 kilometers wide, covered in a crust of carbon and ice. On its sunlit side, jets erupt as warmth seeps in, creating pockets of gas that escape through cracks. On the dark side, frost condenses again, replenishing the surface in a slow, eternal cycle. Around it, dust drifts outward, forming a halo that glows in sunlight, a halo that carries away information, a natural archive of physical data written in the distribution of grains and the composition of gases. To study 3I Atlas, then, is to study both the visible and the invisible, the outer expression and the inner engine. The light gives us the chemistry, but the motion of that light gives us the story of forces, of momentum and balance. Because as we watched the spectra shift and the brightness fluctuate, we also saw something else: the absence of perturbation. No measurable acceleration beyond that, explained by outgassing. No unexpected deviations in its predicted course. Even under the influence of strong solar wind, the path of 3I Atlas remained serene. And this leads us, inevitably, toward the next layer of the mystery: how such a small body, made of fragile ices and dust, could travel through the turbulent environment near the Sun and emerge unscathed. To answer that, we must look outward again, not at the nucleus, not at the coma, but at its journey past the planets, through the invisible currents of gravity and light. Because proximity, in space, is not always influence. Sometimes, what appears close in the sky is far in effect, and what should pull or deflect barely leaves a trace. And so, as 3I Atlas passes near the orbit of Mars, we begin to ask a deeper question: what does it really mean to be close in the cosmic sense? And why does closeness not always lead to change? As 3I Atlas moved inward and crossed the orbit of Mars, the notion of closeness took on a very different meaning. In the language of space, distances that sound immense to us, tens of millions of kilometers, are, in gravitational terms, a hair's breadth. Yet in that same vastness lies a strange serenity. Objects can pass within a few planetary radii of each other and still not exchange more than the faintest tug of force. When astronomers say that 3I Atlas passed near Mars, they mean it crossed the same region of the solar system, not that the planet's gravity pulled at it with any meaningful strength. The truth is more subtle, more poetic. It is about trajectories that weave through invisible fields, where proximity does not guarantee influence, and where even the giants of our solar system can be mere bystanders to a passing interstellar guest. The passage near Mars was one of the most closely observed moments of 3I Atlas's journey. Telescopes around the world, from the deserts of Chile to the ice of Mauna Kea, tracked its motion each night. The challenge was exquisite. The object moved swiftly across the star field, its position changing by arcseconds per hour, demanding precise timing and calibration. Each measurement added a small dot to an ever-growing map, the ephemeris, that sacred table of positions and velocities that defines how something moves through the heavens. In those dots lay the story of whether the comet's path was being perturbed, however slightly, by gravitational nudges or by the pressure of sunlight and gas. What scientists sought, above all, was deviation, a whisper of acceleration that might reveal a hidden influence. Astrometry, the art of measuring positions with almost absurd precision, became the tool for this search. In each frame, 3I Atlas appeared as a fuzzy spot surrounded by pinpoint stars. By comparing its coordinates against those fixed lights, astronomers could refine its orbit with mathematical grace, subtracting errors introduced by the atmosphere, by optical distortion, by the dance of the telescope's own imperfections. It is, in a sense, a dialogue between noise and clarity. Every image is imperfect, yet when hundreds of them are combined, a pattern begins to emerge, the path of a traveler moving through sunlight. And what that pattern revealed was remarkable. The comet's predicted track matched observation almost exactly. Within the limits of our best instruments, 3I Atlas did not waver. The deviations were smaller than the margin of error, smaller even than what one might expect from outgassing or from the faint drag of solar radiation. This stability surprised many, because hyperbolic comets, especially those rich in volatiles, often show small non-gravitational accelerations. As jets of vapor erupt unevenly across their surfaces, they can act like miniature thrusters, altering the orbit ever so slightly. Yet 3I Atlas moved as though no such thrusters existed. The force of its sublimation appeared symmetrical, or perhaps so gentle that it cancelled itself out. It was as if the object had achieved a quiet balance, a symmetry between heating and release that rendered its journey smooth and unwavering. Some astronomers likened it to a sailboat gliding through turbulent seas, yet never listing, never caught by the gusts. Others wondered if its nucleus was larger or denser than first assumed, giving it enough inertia to resist subtle forces. If so, its mass would have to be significantly higher than that of typical comets of similar size. But that would raise another puzzle. How could something so massive still produce such an extensive coma? These questions hung in the air, unresolved, their answers entangled in the interplay between observation and theory. The Mars passage also offered a chance to calibrate the models used to predict the comet's motion. By observing from multiple vantage points, Earth-based observatories, space telescopes, and even instruments aboard orbiters, astronomers could triangulate its position in 3 dimensions. Each dataset carried its own uncertainties. Optical telescopes measure against the star background, while infrared instruments respond to heat signatures that can shift with viewing angle. Bringing them together required careful correction for parallax and timing, for every fraction of a second counts when an object moves at tens of kilometers per second. Yet even after all the corrections, all the alignments, the final trajectory remained consistent. The differences were less than a kilometer, at distances where errors of hundreds would have been acceptable. That kind of precision, achieved through cooperation across continents, was itself a testament to how far our tools have come. But the real beauty of that passage lies not only in its data, but in what it says about the nature of gravitational proximity. In everyday life, closeness brings influence. The nearer you are to a source of force, the stronger its pull. Yet in space, scale changes everything. Gravity diminishes with the square of distance, and when both masses are small, one a planet, the other a cometary nucleus, the actual change in velocity caused by such an encounter can be vanishingly slight. Mars, despite being massive by human standards, is a mere pebble compared to the Sun's dominance. Its gravitational reach is a local ripple on an ocean of heliocentric control. So while the encounter between Mars and 3I Atlas was geometrically near, dynamically, it was distant. Their gravitational fields touched lightly, like two notes in harmony rather than collision. Still, even light touches can be meaningful when measured with enough care. Astronomers examined the residuals, the small differences between predicted and observed positions, looking for trends that might indicate a gravitational tug or a systematic error. Residual plots became the quiet language of their curiosity, points scattered above and below a central line, most within expected uncertainty, some wandering slightly more, yet no consistent drift emerged. The conclusion was almost philosophical: proximity without consequence. The cosmos, it seems, is full of near misses that are not mistakes, but part of the natural rhythm of orbital mechanics. From a different perspective, this steadiness tells us something profound about how precise our understanding of celestial motion has become. To predict an object's path, months or even years ahead, to within fractions of an arc-second, is an achievement of extraordinary subtlety. Every factor must be accounted for: the gravitational pull of planets, the pressure of sunlight, the outflow of gases, the relativistic corrections near the sunday. Each of these terms belongs to an equation that, when balanced, describes reality with astonishing fidelity. And when the data from 3I Atlas agreed with those predictions, it wasn't just confirmation of the model, it was a quiet reminder that nature, even in its complexity, obeys rules we can learn to understand. That understanding is itself an act of connection, a bridge between the mathematics written in human minds and the motion of objects born under alien stars. Yet some could not help but wonder if the perfection was too perfect. Perhaps the lack of deviation was an illusion, a consequence of our own limitations. After all, every observation carries noise from the flicker of the atmosphere, the jitter of instruments, the calibration of clocks. Could small, real effects have been hidden beneath that noise floor? Or might the comet's apparent calmness conceal internal processes that balance out uneven jets automatically? A rotating nucleus, for instance, can average out its own impulses if its spin axis aligns just right. In such a case, the vector sum of outgassing forces could be nearly zero, even though the surface itself is far from uniform. It would be a beautiful coincidence of geometry and physics, a celestial form of self-stabilization. Some speculated about electromagnetic influences, too faint to measure directly, but perhaps strong enough to dampen subtle deviations. The coma, filled with ionized gas, interacts with the solar wind and magnetic field in complex ways. Could these interactions create currents that, while imperceptible on small scales, distribute momentum evenly across the coma, effectively shielding the nucleus from asymmetric pushes? If so, the reason 3I Atlas remained so steady might not be its mass alone, but the dynamic equilibrium of its environment, a kind of electromagnetic cushioning that softened the blows of solar wind. During the Mars approach, another aspect came into play: timing. The comet's position relative to the Sun and planets affected how we could observe it, how light scattered, and how data were interpreted. Astronomers synchronized observations across longitudes, sharing time slots like relay runners passing a torch. In doing so, they built a near-continuous record of its journey. Each data point was a heartbeat, each frame a pulse. When plotted together, they formed a smooth curve through space and time, a mathematical reflection of motion so precise that it felt almost organic. That continuity was crucial, because it allowed scientists to rule out sporadic accelerations. There were none, no sudden jumps, no lingering shifts. Only the steady glide of a visitor moving as if guided by a hidden symmetry. You might imagine, standing under the night sky, watching that faint dot slip past the red planet, how strange it must feel to know that it will never return. Its trajectory, forever outward, means that this was the only time in all of history that 3I, Atlas, and Mars would share the same quadrant of space. After a few weeks, even that closeness was gone, the comet moving on, leaving behind only lines on charts, numbers in tables, and a growing sense of awe at its indifference to gravitational drama. And yet, what follows this serenity is not emptiness but curiosity, because as 3I Atlas continued deeper into the sun's influence, it crossed into regions of light so intense that direct observation became difficult. The glare of the sun overwhelmed ordinary instruments. To follow it further required a different kind of eye, a way to see what lies behind the brightness itself. Coronagraphs, those ingenious devices that mimic an eclipse by blocking the solar disk, would become our next window. Through them, the comet could be traced even as it passed near the sun's blinding halo. The story was moving inward now, into the very heart of light, where our instruments must become more clever and our patience more exacting. Because to see an object behind the sun is not just a feat of technology, it is a metaphor for the persistence of curiosity itself, the human will to look beyond the glare into the hidden geometry of the cosmos. There is a moment, brief but breathtaking, when an object in the inner solar system slips behind the Sunday from Earth. It vanishes into radiance. The sky turns into a curtain of light, and all that remains is the glare unbroken, absolute. For 3I Atlas, this crossing was inevitable. Its hyperbolic path carried it close enough that the sun's brilliance would swallow it from view for weeks. No ordinary telescope could follow it then. The vast instruments that had traced its arc through the stars found nothing but blinding whiteness. And yet, as so often happens in astronomy, invisibility only deepened the desire to see. To watch a comet move behind the sun is to confront one of the oldest challenges in observational science, the challenge of looking through light itself. The solution, as elegant as it is counterintuitive, came from human ingenuity, the coronagraph. Invented to mimic the natural eclipse, a coronagraph places a small disk in front of the sun's image, blocking its central brightness while revealing the faint corona that surrounds it. In that region where the light is dimmer, where the magnetic fields of the sun twist and shimmer like slow lightning, an object as small as a comet can sometimes be seen, if one knows where to look. When 3I Atlas entered that zone, the coronagraphs aboard spacecraft such as SOHO and Stereo began to watch. These instruments orbit close enough to the sun to observe continuously, providing an uninterrupted vigil as the interstellar traveler approached conjunction. Against the backdrop of the corona's streaming light, astronomers searched for a single moving point, a streak that should glide along the precise curve predicted by the ephemeris. That prediction had been refined over months, using data from before the comet disappeared. Now it would be tested against the most unforgiving environment imaginable. Imagine those images, frames filled with the ghostly tendrils of plasma, the corona pulsing in slow motion, magnetic loops rising and collapsing. Somewhere within that glowing chaos, a thread of motion, a tiny, shifting shadow, would betray the comet's presence. It was like watching a moth cross the face of a bonfire, the faintest interruption of brilliance. The process was painstaking. Automated algorithms scanned thousands of frames, aligning them, subtracting solar glare, hunting for patterns of consistent movement. But the final confirmation still came from the human eye. Astronomers traced a thin, slanted line through the noise, the same arc the models predicted days before. 3I Atlas was there, alive, intact, and still on course. This kind of observation is an act of faith as much as of physics. The sun's corona is not static. It changes moment to moment, sculpted by magnetic storms and waves of charged particles. Any given feature might masquerade as motion. The comet's faint tail, if visible at all, would blend into the coronal filaments that themselves stream away at hundreds of kilometers per second. To find a moving object in such a field is like finding a specific ripple on the surface of a boiling sea. And yet, through patience and mathematics, the scientists succeeded. The track of 3I Atlas emerged, not as a bright line, but as persistence, the same subtle streak appearing in multiple frames, moving with the right rhythm, in the right direction, at the right time. What the coronagraphs revealed was more than position. They hinted at interaction. As the comet crossed behind the sun, subtle fluctuations in the brightness of the surrounding plasma were recorded brief dimmings and brightenings that corresponded with the comet's expected path. Some interpreted these as noise, others as possible evidence of magnetic disturbances. If true, they could mean that 3I Atlas's coma, though invisible against the solar glare, was still coupling faintly with the sun's magnetic field, disturbing the delicate loops of plasma that rise and fall through the corona. To prove such a thing would require precision beyond current instruments, yet the idea itself was tantalizing, an interstellar traveler momentarily brushing the skin of our star. For observers on Earth, the days of conjunction were filled with waiting. The comet was gone from the night sky, lost to daylight. Its path was now purely a matter of calculation numbers flowing through equations, predicting what no eye could confirm. Yet those numbers carried weight. Each update from the coronagraph extended the ephemeris forward, shrinking uncertainties. It was as though a thread of logic stretched across the solar blaze, unbroken. Even without direct light, the mathematics continued to see, and then, gradually, 3I Atlas emerged from the other side. When the sun's glare finally loosened its hold, faint reports began to arrive. Small observatories in the southern hemisphere caught a hint of motion just above the horizon before dawn. The comet reappeared, right where the models said it would be neither delayed nor deflected, its orbit unchanged. It had passed through the domain of the sun unscathed. The question that had haunted astronomers since its discovery returned stronger than ever. How could it endure so much radiation, magnetic storms, even coronal mass ejections, and yet remain steady, indifferent, precise? To understand what it endured, we must imagine the environment it crossed. The corona, though ethereal, is violent. Its temperature reaches millions of degrees, though its density is low. Magnetic fields coil and reconnect there, unleashing eruptions that can fling billions of tons of plasma into space. These coronal mass ejections travel at speeds up to 1,000 kilometers per second, dragging with them magnetic fields that can extend across millions of kilometers. A comet passing through such a region is exposed to currents and pressures no spacecraft could survive. Theoretically, its coma should compress, its ion tail should twist, perhaps even detach entirely. But 3I Atlas, according to both observation and prediction, suffered none of these in ways that altered its course. Its coma may have flared, its tail may have danced, but its nucleus, that silent, dark core, held its line. There's something almost defiant about that. The sun throws everything it has: light, wind, magnetism, and the interstellar guest simply passes through, acknowledging nothing. It's a reminder that scale matters in ways we rarely grasp. The forces that seem overwhelming to us are, on the cosmic stage, often gentle. The solar wind that can disable satellites would barely nudge a mountain-sized comet. Even the energy of a coronal mass ejection, spread across its vast front, might impart less total momentum to the nucleus than a falling leaf would feel in a breeze. Yet there is still mystery in how perfectly these forces cancel, how the chaotic solar environment leaves the trajectory untouched. The images from coronagraphs, when assembled into time-lapse sequences, show the comet's faint track moving behind shifting curtains of plasma. Each frame is a fusion of light and mathematics, the visible trace of the invisible. Scientists overlay the predicted path, frame by frame, watching as the dots of brightness align. Sometimes the path crosses a flare, sometimes a coronal streamer, sometimes open space. The consistency of its motion through all of this is what astonishes most. It is as though the universe had drawn a line across chaos and dared anything to erase it. Nothing did. And in this act of tracing, of following an almost invisible traveler through blinding light, there is a quiet metaphor for human curiosity itself. We have learned to see through the sun, to build instruments that can stare into brightness without being blinded. That ability to look at what cannot be looked at is one of our greatest achievements. Coronagraphs are not just devices, they are expressions of our will to perceive, to push the boundaries of light and reason. Through them, we caught glimpses of 3I Atlas, even when it was hidden, and those glimpses affirmed something both simple and profound, that the laws of motion, the quiet reliability of physics, hold true even in the furnace of the sun's breath. Yet beneath that calm truth lies a deeper question. If 3I Atlas's trajectory was untouched by the sun's violence, does that mean its coma and tail were immune as well? Or did subtle transformations take place, changes too delicate for our coronagraphs to see, but significant in the realm of plasma and magnetism? Some reports hinted at minor fluctuations in brightness patterns before and after conjunction, as though the coma had been momentarily compressed or reshaped. These hints, faint though they were, led scientists to wonder about the precise nature of solar interaction. Was it merely thermal, or did electromagnetic coupling play a role? Could the comet's passage through a magnetic region create localized disturbances, microshocks, eddies, perhaps even reconnections? The answers remain incomplete, suspended between observation and speculation. But what matters most is that 3I Atlas survived its journey through the sun's veil intact, its motion a perfect continuation of the same hyperbolic curve drawn months earlier. Its reappearance was not just a scientific confirmation but an emotional one. There was a moment when the first post-conjunction images arrived, where astronomers around the world felt the same quiet thrill, the relief of recognition. There it was, faint but unmistakable. The visitor had come through. And with that reappearance came a new opportunity. The comet, now outbound, would soon begin to cross paths with streams of solar material, again streams far more structured and forceful than the smooth background wind. Coronal mass ejections, still radiating from active regions of the sun, would sweep across space like invisible storms. The question now was what would happen when one of these massive clouds of magnetized plasma collided directly with the coma of 3I Atlas. Would it finally bend? Would its ion tail ripple and snap, as others have before? Or would it continue, as always, undisturbed, an interstellar stone passing through a sea of fire? The coronagraph observations had brought us to the edge of that encounter. They had shown us the sun's luminous wall and the faint trace of a traveler beyond it. What came next would test our understanding of both solar fury and cosmic endurance. Because to grasp what happens when the sun strikes an interstellar visitor, we must step beyond light itself, into the invisible architecture of plasma, into the geometry of storms we cannot see but only feel in the trembling of magnetic lines. And that is where the next part of the story begins, in the realm of coronal mass ejections, where light gives way to motion and the true collisions of the cosmos unfold. If you could see the sun not as a glowing disk, but as it truly is, a vast, boiling ocean of plasma, you might understand how fragile everything near it becomes. Every second, loops of magnetic energy twist and snap across its surface, releasing bursts of light and streams of charged particles that to sweep through the solar system. These outbursts are not random flashes, they are the pulse of a living star, and sometimes the pulse quickens. When magnetic fields deep within the corona suddenly reconnect, they fling out colossal clouds of plasma coronal mass ejections, or CMEs, waves of matter and magnetism traveling through space at hundreds, sometimes thousands, of kilometers per second. Unlike solar flares, which are bursts of electromagnetic radiation, CMEs are physical events, immense bubbles of charged gas hurled outward, carrying with them tangled magnetic fields. They can be vast enough to envelop entire planets, wide enough to stretch millions of kilometers across. In the darkness between planets, these magnetic storms carve invisible boundaries, reshaping the flow of solar wind, compressing it, and sometimes even reversing its direction. They are, in a sense, the breath of the sun, expelled in convulsions that ripple through the heliosphere. When one of these waves moves through interplanetary space, it drags the interplanetary magnetic field along, distorting the geometry of space around it. Earth's magnetosphere feels these events as geomagnetic storms. Spacecraft record spikes of radiation and particle flux. But for a small, fragile body like 3I Atlas, a CME represents something more intimate, an encounter between a moving solid and the invisible weather of the cosmos. To imagine such a meeting is to picture two vastly different worlds, one made of frozen gases and ancient dust, the other of fire and magnetic force. And yet, that meeting did happen. During the weeks following the comet's passage behind the Sun, the solar surface erupted 3 times in quick succession, launching waves of plasma into the same quadrant of space through which 3I Atlas was traveling. Each CME differed in size and energy, but all were powerful enough to alter the solar wind density and magnetic field for millions of kilometers around. Predictive. Models placed at least one of these ejections on a direct collision course with the comet's path. It was a rare alignment, the kind of coincidence that observational astronomers dream of. Here was a natural experiment, an interstellar visitor, unbound by the Sun's gravity, about to be struck by the full force of its magnetic breath. What happens when a CME meets a comet has been observed before, but never under circumstances quite like this. In 2011, for example, NASA's Stereo spacecraft recorded a CME striking comet Lovejoy. The collision compressed its coma, distorted its ion tail, and for a moment seemed to tear it apart. The tail snapped, then reformed downstream, a shimmering scar in the solar wind. These events reveal a simple truth. Comets, though fragile, respond vividly to changes in plasma. Their ion tails, being made of charged particles, are directly linked to the magnetic field lines that thread through space. When a CME passes by, those lines can bend, twist, or even break, dragging the tail with them. In the case of 3I Atlas, however, the results defied expectation. Spacecraft watching from afar recorded the solar storms in exquisite detail. Models showed that one CME, with an average velocity of 600 kilometers per second, swept through the region of space the comet was predicted to occupy. The timing was perfect, or, from another perspective, ominous. Yet when telescopes later recovered the comet, its orbit showed no measurable deviation. No sudden change in brightness, no displacement in trajectory, no evidence that it had been significantly disturbed. The storm had passed, but the traveler had not flinched. To understand why this is extraordinary, we have to think about the forces involved. A CME carries both mass and momentum. Even though its density is low by earthly standards, less than a billionth that of air, its total mass, spread across its enormous size, can reach billions of tons. When it strikes an obstacle, it transfers a portion of its energy and momentum, much like wind striking a sail. The amount of deflection depends on the density of the plasma, the cross-sectional area of the object, and the duration of impact. In most cases, the effect is small but measurable. But with 3I Atlas, the expected deviation simply wasn't there. The CME, by all calculations, should have produced at least a whisper of acceleration. Yet the comet moved as though nothing had touched it. Perhaps then, the encounter was more subtle than a simple impact. Plasma, after all, does not behave like air or water. Its motion is governed by magnetic fields, and those fields can slip around objects, wrapping them in currents that deflect energy rather than absorb it. If the coma of 3I Atlas was sufficiently ionized, it might have acted as a kind of buffer, a magnetic cushion that distributed the incoming pressure evenly around the nucleus. In that case, the CME would have compressed the coma, brightened it briefly, then flowed on, its momentum absorbed, not mechanically, but electromagnetically. The nucleus would have felt almost nothing. And indeed, faint traces of such compression may have been recorded. A few instruments detected a brief increase in the brightness of the comet's ion tail at the time of the CME's passage, followed by a swift return to normal levels. This was interpreted by some as the signature of a tail disconnection event, where magnetic reconnection severs part of the ion tail, releasing it into space. In other comets, such disconnections are dramatic, leaving visible gaps. For 3I Atlas, the change was barely perceptible, a flicker, no more. If a disconnection did occur, it was remarkably contained, suggesting that the interaction between the CME and the comet was brief, localized, and quickly self-correcting. What fascinates me about this is the balance it reveals between violence and harmony. The CME, a storm of unimaginable energy, meets a body of dust and ice, and instead of chaos, there is balance forces distributed so perfectly that they leave no trace in the motion of the whole. It's a reminder that the universe is not only a place of destruction, but also of delicate equilibrium, where even the fiercest energies can find a way to pass through without breaking what they touch. And yet, this serenity raises deeper questions. If the CME imparted no measurable impulse, does that mean the coma truly shielded the nucleus? Or was there something about the comet's own structure that resisted external influence? Could its mass have been greater than estimated, or its composition more cohesive than expected for a body of interstellar origin? If its density were unusually high, its inertia could easily overpower the subtle pushes of solar plasma, but that explanation alone feels too simple. The patterns of its ion tail, the uniformity of its coma, and the steadiness of its motion suggest something more dynamic, an interaction that self-regulates, that adapts. Perhaps the key lies in the magnetic field itself. As a CME passes, it carries with it regions of differently oriented magnetic polarity. When these fields encounter the ionized gases around a comet, they can induce currents, loops of electrical energy that flow through the coma. These currents, in turn, generate their own magnetic fields, which oppose the incoming ones, softening their impact. It's a process known as magnetic shielding, and while it operates on scales small compared to planets, it can still be powerful enough to reduce the net force on the nucleus to almost zero. If 3I Atlas possessed such a self-generated magnetic envelope, it would explain why it seemed to glide unharmed through multiple storms. In laboratory terms, we might call this a plasma interaction zone, a region where the magnetic fields of the solar wind and the comet's own environment become entangled, exchanging energy without direct collision. Within that zone, particles are accelerated, currents fluctuate, and energy is dissipated in waves rather than shocks. For an observer far away, the effect would be invisible, masked by the comet's faint luminosity. But for the object itself, it could mean the difference between turbulence and tranquility. There is also a geometric factor to consider. The CME, vast though it was, may not have struck the densest part of the coma head-on. If its trajectory intersected only the outer layers, the faint halo of ions trailing behind the nucleus, then the energy transfer would have been diffuse, spread across millions of kilometers. The comet's motion would continue almost unchanged, its course bent only infinitesimally, below the threshold of detection. Yet the plasma surrounding it would still react, producing the transient effects observed in its tail. In that sense, the CME did touch it, but only gently, like wind brushing a mist. In the days that followed, as the comet receded from the sun, further CMEs erupted, some directed away, others tangentially across its path. Each time, astronomers watched for evidence of change, a shift in trajectory, a surge in brightness, a distortion of the tail. Each time, they found the same calm persistence. The orbit remained true. The interstellar visitor, unbound and unbothered, continued on its long arc outward. It had taken 3 massive hits from the sun itself, and the result was not chaos but continuity. And perhaps that is the most humbling revelation. For all the power of our star, for all the storms that can light up worlds and shake magnetic fields across planets, an object the size of a mountain, born from another sun, passed through unbroken. It did not resist the sun's might, it simply transcended it, moving through as though following a law more subtle than gravity or magnetism. But what if those subtle laws are precisely what we have yet to understand? If the behavior of 3I Atlas cannot be fully explained by mass, geometry, or plasma dynamics, then perhaps there are missing terms in our equations, small, hidden effects that only emerge under the rarest of circumstances. To find them, we must look closer, not at the grand collisions, but at the microscopic interactions where charged particles and magnetic fields intertwine. Because in those quiet, invisible exchanges, we might discover the secret of how an interstellar visitor could pass through the heart of a solar storm and continue untouched. And so, the path of 3I Atlas carries us onward from the macrocosm of the sun's rage to the microcosm of its effects, from the spectacle of coronal eruptions to the invisible architecture of momentum and balance. To truly understand why it did not bend, we must now turn to the mathematics of motion itself, to the problem of momentum, and to the question of how much, if anything, those solar strikes could have shifted the course of a traveler from another star. When we speak of collisions in the cosmos, we must be careful. Most of what we call an impact in space is not a solid meeting of matter, but a transfer of energy, a conversation between forces spread thin across unimaginable distances. The encounter between a coronal mass ejection and 3I Atlas was one of these. To the eye, it may have looked like nothing at all, a ghostly brush of light across the void. But to the physicist, it posed a riddle. If the sun hurled 1 billion tons of plasma into the path of a comet, where did the momentum go? Momentum is one of those concepts that seems simple when we learn it. Mass times velocity, the product of motion itself. But in the vastness of space, where densities are vanishingly small, momentum takes on a more ethereal form. It becomes something distributed, spread across countless particles and fields, passed from one structure to another like a ripple moving through fog. To estimate how much the CME might have changed 3I Atlas's course, scientists had to construct a model, not an image, but a framework of orders of magnitude, a hierarchy of forces. The nucleus of 3I Atlas, based on its brightness and inferred density, was likely a few kilometers across. If we imagine it as a sphere of ice and rock, perhaps 3 kilometers in radius, its volume would be about 113 cubic kilometers. Assuming a density close to 500 kilograms per cubic meter, typical for porous cometary ice, that would give a total mass on the order of 50 trillion kilograms. A staggering number by human standards, yet in cosmic terms, a pebble. Now, consider a CME. Though it spans millions of kilometers, its density near 1 astronomical unit, the distance from the Sun to Earth, is only about 10 particles per cubic centimeter. When translated into mass per unit volume, that becomes roughly 10 to the power of minus 20 kilograms per cubic meter. Spread over its enormous front, however, the total mass of a CME can reach billions or even tens of billions of tons. When that moving cloud of plasma passes through a region containing the comet, only a tiny fraction of its total mass interacts directly the portion that sweeps across the comet's coma, whose effective cross-section might extend 100,000 kilometers in radius. The result is a paradox of scale, enormous energies meeting almost negligible coupling. If one calculates the impulse, the change in momentum transferred, using optimistic values for density, speed, and interaction duration, the shift in velocity imparted to the comet's nucleus would be no more than a few millimeters per second. That's 1,000 times smaller than what current astrometric measurements can detect. In other words, even a direct hit would hardly move it, yet physics rarely offers clean lines. What complicates this picture is that plasma does not act like an ordinary fluid. The CME's magnetic field interacts with the charged particles in the coma, creating a drag force not through mechanical contact, but through induction. The question becomes one of coupling efficiency. How much of the CME's momentum is actually transmitted through electromagnetic processes? If the field lines connect with the comet's environment, the drag could increase dramatically. If they slide past without reconnection, the effect could be almost nil. In the case of 3I Atlas, the evidence leans toward the latter, a fleeting connection, then release. Astronomers, in their effort to quantify this, built models of several scenarios. In the most optimistic case, a CME directly intersecting the densest region of the coma. With perfect coupling and full momentum, transfer, the resulting acceleration might have nudged the comet's velocity by about 1 centimeter per second. It sounds small, but over weeks, such a deviation could grow measurable. However, no such deviation was observed. The real value, then, must have been smaller, perhaps closer to 1/10,000th of that, and that leads to the deeper realization that what saves the comet from disturbance is not defiance, but geometry. The CME, though immense, is diffuse. The comet's nucleus, though solid, is minuscule. The two are misaligned in almost every possible sense. The plasma wave passes by, envelops the coma, exerts a whisper of force, and moves on. The total change in the nucleus's momentum is practically zero. The only visible trace is in the behavior of the ions, their tails bending, their emission brightening for a moment before returning to equilibrium. Still, the precision of the data invites imagination. Suppose, for the sake of thought, that the comet were lighter, say a tenth of its estimated mass, or that the CME had been denser, perhaps 10 times what we expect. In that case, the shift might have reached measurable levels, perhaps enough to alter its orbital prediction by seconds or minutes. Even then, though, the deviation would remain infinitesimal compared to the grand sweep of its hyperbolic flight. Momentum, in these terms, becomes a whisper lost in the roar of motion. What fascinates me is how this simple exercise, balancing energy and mass across scales, illuminates the delicate machinery of the cosmos. We are used to thinking of explosions and collisions as decisive, as moments of irreversible change. But here, the collision is almost philosophical. Energy meets inertia, chaos meets order, and the outcome is silence. The comet continues, unchanged in its path, but altered, perhaps, in ways too fine to see its coma reshaped, its particles recharged, its field rethreaded by invisible lines of magnetism. In the equations, this process can be expressed as an integral of force, over time, the impulse delivered across the encounter. But in reality, it is less a sudden push than a negotiation, a dynamic exchange between charged clouds. Every atom of the CME's plasma carries its own momentum vector, and when it interacts with the coma's ions, those vectors scatter in countless directions. The net result averages to almost nothing, not because the forces are weak, but because they cancel. Symmetry becomes protection. And perhaps this is why 3I Atlas's path remained so stable. Its coma, vast and diffuse, acted not as a target, but as a buffer. The more space the ions occupied, the more evenly distributed the incoming forces became. In a strange way, its vulnerability, its tendency to shed material, to diffuse into gas and dust, became its strength. By spreading itself across a wide region, it diluted the impact of the solar storm. This principle, that dispersion can create resilience, echoes throughout nature, from galaxies to ecosystems. What breaks easily when compact often survives when scattered. Astronomers noted this with awe. When they plotted the post-CME trajectory, they found the deviations smaller than the smallest error bars. The line between prediction and measurement was, in effect, the same line. For all practical purposes, nothing had changed. But in that nothing lay a profound message. Even when struck by forces that would dwarf entire planets, the comet's course remained governed by the simplest law of motion, that a body continues in its path unless acted upon by a net external force. Newton's principle, written centuries ago under candlelight, held true beneath the fury of the Sunday, yet we are left with an itch that mathematics cannot soothe. What if the absence of measurable deviation is not because no force acted, but because multiple forces acted and cancelled one another? The CME, after all, was not one uniform flow but a complex structure, filled with eddies and counterstreams of magnetic polarity. If one wave compressed the coma from one side, while another pulled from the opposite, the resulting impulses could sum to zero. The nucleus, caught between equal pressures, would feel balance even amidst chaos. This possibility points toward the next layer of inquiry, the composition and configuration of the plasma fields themselves. The sun's outflows are not single events. They are networks of tangled flux ropes, each carrying current and magnetic tension. When such a structure encounters a conductive environment like a comet's coma, the two can become linked briefly, exchanging energy through magnetic reconnection before snapping apart again. Each reconnection event can produce local acceleration, yet the directions vary randomly. Over time, these random accelerations may cancel, leaving the nucleus apparently undisturbed. To capture such effects requires simulations far beyond simple analytic models. Magnetohydrodynamics, the physics of how magnetic fields and plasma move together, becomes the key. In these simulations, the comet is no longer a static sphere, but a dynamic conductor, surrounded by flowing currents and induced fields. When a CME sweeps past, vortices form, currents, close, and waves propagate through the plasma. The total force on the nucleus emerges not from any single event, but from the balance of many small, opposing ones. And when those sums even out, the result is exactly what we observe: calm motion through apparent chaos. One might think of it this way: the comet did not resist the sun, it resonated with it. Its environment adapted to the solar wind in such a way that stress and release happened simultaneously. The CME's energy did not vanish, it was absorbed, redistributed, and released through the comet's tail, through ion flows and radiation, leaving the solid core untouched. What we call no deviation is, in truth, an intricate choreography of compensation. It's humbling to think that what looks like simplicity, a clean hyperbolic path, a constant speed, can be the outcome of complexity so deep we can barely trace it. The mathematics that describe such balance verge on the poetic. Systems that appear inert are in fact alive with invisible motion. And this invisible motion hints at a wider truth, one that will lead us into the next stage of our inquiry. Because if the comet's momentum remained unchanged, we are left with two possibilities. Either the sun's storms were never strong enough to matter, a question of scale, or some deeper mechanism, hidden within the physics of plasma and magnetism, ensured that their effects cancelled. The next step, then, is to explore those mechanisms to see whether geometry, composition, or sheer chance explains the perfect stillness of motion we have observed. And perhaps, as we follow those threads, we will find that what protects a comet from the sun's storms is not luck at all, but the quiet order that underlies even the most turbulent skies. When faced with a mystery in nature, the first instinct of science is not to leap toward the extraordinary, but to build carefully within the ordinary. Before invoking exotic forces or new physics, we return to the models we know: geometry, inertia, magnetic fields, the quiet logic of vectors. And so, after 3I Atlas took 3 solar impacts, yet kept its perfect path, astronomers began the patient process of sorting through what might be called the conventional explanations. Not the miraculous, but the mechanical, not defiance of the sun's will, but the subtle fulfillment of it. 3 possibilities rose to the surface, each grounded in established physics, each simple enough to be believable, yet delicate enough to leave room for wonder. The first was geometric. Perhaps the CMEs, vast though they were, had simply missed the nucleus. The second was structural. Maybe our estimates of 3I Atlas's mass and density were wrong, and its inertia was far greater than we thought. And the third was statistical. What if multiple impacts, arriving from slightly different directions, produced impulses that cancelled each other, leaving the net force close to zero? 3 paths through familiar terrain, each pointing toward the same horizon: stability without mystery. The geometric argument begins with a subtle truth. Space, though immense, is mostly angles. The CME that sweeps across the solar system is not a solid front, but a curved, uneven wave. It has thickness, layers, and structure. Some regions carry strong magnetic fields, others are almost empty. When this wave encounters an object like a comet, the effect depends entirely on alignment, whether the densest part of the plasma passes through the densest part of the coma. If the CME glances off at an angle, striking only the outer halo of ionized gas, then most of its energy slips past, like wind brushing the edge of a cloud. Observational evidence supports this possibility. The modeling of CME trajectories, reconstructed from spacecraft data, shows that at least 2 of the 3 ejections approach from slightly oblique directions. They were not head-on, but offset by tens of degrees. That means the densest core of the plasma likely missed the comet's nucleus entirely. In such a case, the forces on the coma would have been asymmetric but weak, enough to disturb the tail temporarily, but not enough to alter the trajectory of the whole. The nucleus would have sailed through a thinning region of the wave, experiencing little more than a faint squeeze, a soft magnetic ripple that left its course unchanged. There's something quietly elegant about this idea that the very geometry of space, the accident of angles and timing, might protect a traveller from the violence of a star. Nature, after all, rarely acts in straight lines. The sun's outflows are spirals, the comet's path a curve, and in the meeting of curves, there is always the possibility of avoidance. Even when events seem inevitable, the universe finds space for grace. The second explanation reaches deeper into the comet itself, into the weight of its being. When we estimate a comet's mass, we rely on light, its brightness, its albedo, the behavior of its coma, but these are indirect signs. If 3I Atlas were denser than we think, perhaps because it contained less porous material or more rock than ice, its inertia would be enormous. The same CME that could buffet a smaller comet might barely move one with higher density. Our models assume a standard density for cometary nuclei, derived from measurements of those born in our own solar system. But 3I Atlas is an interstellar visitor, shaped under a different sun, by different pressures and temperatures. Imagine a body forged in a colder disk, where ice is condensed under greater pressure and voids were few. Its structure would be more compact, its molecules arranged with the tightness of stone rather than snow. Such an object would resist both heat and motion with quiet tenacity. It would not sublimate easily, it would not tumble under the influence of uneven jets. It would hold its shape and mass like a deep-sea stone dropped into air. In that case, even the cumulative push of 3 CMEs would barely register against its momentum. The difference between a slight nudge and no movement at all would be swallowed by the comet's immense inertia. There's an appealing simplicity to this view, too, not an invisible shield, not a mysterious equilibrium, but sheer stubborn mass. The universe, after all, often hides its secrets in density. And perhaps this is the lesson 3I Atlas brought, that even in the thinness of space, substance still matters. The third explanation is perhaps the most poetic, though it arises directly from mathematics. When multiple forces act on an object from different directions, their vectors can cancel, leaving no net effect. The 3 CMEs that erupted during the comet's passage were not identical. They came from different latitudes on the Sun, launched at different angles, each carrying its own magnetic polarity. One approached slightly from above the ecliptic, another from below, and the third from a more equatorial region. If their impulses arrived out of phase 1, pushing northward, another southward, the third slightly west, then their effects could easily nullify one another. The Sun, in this picture, becomes a conductor of cosmic harmony, its storms overlapping like chords in a song. The result is not chaos, but an average, a stillness born of competing tempests. In the numbers, this is easy to show. The vector sum of 3 impulses at near right angles can produce a resultant close to 0. But in the imagination, it becomes something deeper, a vision of balance in motion, of a universe that, even in turbulence, tends toward calm. Yet these 3 explanations, while satisfying, each demand an element of chance. The geometry had to align just so. The mass had to be just high enough. The impulses had to cancel precisely. The likelihood of all these conditions coinciding is small, not impossible, but statistically rare. The scientists who modeled these scenarios admitted as much. In their reports, they described it as a fortunate geometry, a coincidental vector cancellation, a narrow window of parameter space, words that, while cautious, hint at a deeper curiosity. Could it really all be luck? This is where the story turns from certainty to contemplation. Because when nature performs the improbable more than once, we begin to suspect that what looks like luck is really law in disguise, a principle not yet formalized, a pattern not yet named. The data show that 3I Atlas did not behave anomalously, it behaved consistently. It absorbed 3 separate solar impacts without measurable deviation, and it did so while other, nearer comets exhibited visible disturbances under lesser conditions. That contrast suggests that the difference lies not in chance, but in intrinsic properties of structure, composition, or interaction. So, perhaps the truth lies in a blend of the three ideas. The geometry of the CME trajectories might have limited the severity of impacts. The comet's high density could have provided resilience, and the overlapping vector effects could have minimized the cumulative impulse. Together, these factors form a web of natural balance, the kind that arises not from design, but from the sheer complexity of physical law. The universe, when seen closely, often reveals this kind of equilibrium, forces opposing forces, outcomes converging toward stability. Still, one cannot help but feel that something more might be at play, because the interactions between magnetic plasma and conductive bodies are not yet fully understood. The physics is well established in broad strokes: magnetic reconnection, induced currents, pressure gradients, but the details of how these combine around irregular, porous shapes like cometary nuclei remain elusive. Laboratory experiments can model some aspects, but not the full scale, not the interplay of millions of kilometers and nanotesla fields. And so, while the geometric and inertial explanations hold, they do not close the case. They describe how stability might arise, but not entirely why it did so here, under such specific and energetic conditions. That why leads naturally into the next frontier, into the domain of electromagnetic interaction itself, the microphysics of plasma coupling that bridges the visible and the invisible. When I think of 3I Atlas in that light, I imagine its coma as a living membrane, a field of charged particles constantly reconfiguring itself in response to the solar wind. Each ion within it feels the sun's magnetic hand, and each responds not alone but collectively, forming waves and currents that can deflect energy, like ripples reflecting ripples. The nucleus inside becomes less an isolated object and more a node in a vast web of plasma behavior. If that web adapts dynamically to the incoming flow, if it can reshape itself, reorienting its internal currents to distribute stress evenly, then it would act as a kind of organic shield. Not invulnerable, but responsive. Perhaps that is where the secret lies. Not in mass or geometry, but in interaction. The universe, after all, is not built from separate parts, but from relationships. The sun, the CME, the comet, these are not isolated entities, colliding in emptiness, but parts of a continuous field of forces, each modifying the other in real time. What we call a hit might, in truth, be a handshake, an exchange of energy that leaves both participants changed, though neither appears to move. And so, as we trace the fading path of 3I Atlas through the sun's domain, the question evolves. It is no longer simply why the comet did not deviate, but what kind of connection exists between magnetic storms and the bodies that pass through them. Could the sun, in its restless magnetism, interact with interstellar visitors in ways we have yet to comprehend? Could such interactions, subtle and fleeting, reveal something deeper about how fields and matter communicate across the cosmic void? To answer that, we must turn our gaze inward into the physics of contact itself, the electric and magnetic interfaces, where plasma meets solid, where charged particles and conductive surfaces negotiate balance. Because it is there, at the smallest scales, that the great stability of 3I Atlas might find its truest explanation, not in luck or coincidence, but in the quiet logic of electromagnetic harmony that shapes both stars and the visitors that wander among them. When plasma meets a solid, something extraordinary happens, not a collision in the ordinary sense, but a dialogue between charged worlds. At the boundary where the solar wind presses against a comet's coma, space itself begins to glow with invisible structure. Fields bend, currents form, and the faint hum of electricity threads through the silence. This is where the physics of magnetism and motion come together, where matter and light exchange information without ever touching. For 3I Atlas, these interactions define the most certain layer of the story, the electromagnetic frontier, the place where certainty ends and speculation begins. Every comet, whether born in our solar system or beyond it, carries with it a miniature magnetosphere, a fragile, transient bubble carved out of the solar wind. As the charged particles streaming from the sun encounter the gases expanding from the comet's nucleus, they slow down, diverted by electromagnetic forces rather than by mechanical resistance. The result is a boundary, the bow shock, where the solar wind first feels the presence of the comet. Beyond that lies a thinner, more delicate region known as the contact surface, or the cometal pores, where magnetic pressure from the Sun and the outflowing plasma from the comet reach equilibrium. It is there, in that shifting frontier, that the true interaction takes place. Spacecraft have crossed such regions before. The Giotto mission at Halley's Comet, the Rosetta orbiter at 67P, and the Vega probes decades earlier all recorded the same essential pattern. As the solar wind approached, its magnetic field intensified, draped around the coma like fabric caught in the wind. At the same time, currents were induced within the plasma of the coma itself, electric loops that mirrored and opposed the incoming field. Between them, a thin layer formed, less than a few hundred kilometers thick, where the two fields met and cancelled. This layer behaves like a shock, but a soft one, where energy is not destroyed but redistributed. In this boundary zone, the comet becomes something more than ice and dust. It becomes a conductor, a participant in the electromagnetic life of the solar system. The ions streaming from its surface are guided by magnetic lines that curve and twist, forming structures that can stretch millions of kilometers. These structures, when illuminated by sunlight, create the glowing ion tail we see from Earth. Every flicker in that tail is a response to changes in the magnetic field around it, a record of space weather written in light. For 3I Atlas, the evidence of such electromagnetic coupling is beyond doubt. Even from afar, telescopes captured the faint blue hue of its ion tail, the spectral signature of carbon monoxide ions and diatomic carbon excited by solar radiation. The tail pointed directly away from the Sun, straight and narrow, behaving precisely as theory predicts for an object immersed in a well-ordered solar wind. This is the hallmark of magnetic control. The tail's motion reveals not just the direction of the Sun's influence, but its character, its strength, its rhythm, its fluctuations. At times, subtle ripples were observed along that tail, oscillations that corresponded closely with known variations in the interplanetary magnetic field. These ripples, like waves on a flag, confirm that 3I Atlas's coma was actively coupled to the solar environment. When the solar wind speed changed, so did the shape of the tail. When the magnetic polarity flipped, so too did the ion emission pattern. Such coordination cannot be coincidental. It is the language of plasma physics, spoken across millions of kilometers. But beyond the beauty of these observations lies a simple, measurable certainty. Electromagnetic interaction transfers momentum and energy in ways we can calculate. The bow shock acts as a brake on the solar wind, decelerating it slightly as it diverts around the comet. That deceleration generates currents, which in turn produce magnetic fields that oppose further compression. In effect, the coma defends itself electromagnetically. This is the fundamental mechanism behind what we might call plasma shielding. The kinetic pressure of the solar wind is converted into magnetic and electric tension, absorbed by the coma's extended structure rather than transmitted to the nucleus. This process is not speculative. It has been measured directly. The Rosetta mission, for instance, detected magnetic fluctuations and induced currents around 67P that perfectly matched theoretical expectations. Instruments recorded waves propagating along the boundary, the so-called Whistler modes, driven by electrons spiraling along field lines. These signatures were proof that the coma was a dynamic electromagnetic system capable of resisting and reshaping the solar wind. 3I Atlas, though never visited by a spacecraft, would have behaved in the same way, only at larger scales and greater speeds. Its high velocity through the heliosphere would have enhanced these effects, creating a more pronounced bow shock and a more energetic interaction region. What makes 3I Atlas unique is not the presence of these effects, but their apparent perfection. The interactions we know must occur did not result in instability or deviation. Instead, they achieved equilibrium almost instantly. The comet's electromagnetic boundary seems to have adjusted seamlessly to each change in the solar environment, maintaining balance with remarkable precision. This kind of dynamic stability is not mysterious. It is exactly what plasma physics predicts when a system finds resonance with its surroundings. Resonance, in this context, means that the natural timescales of the comet's response match the variations in the solar wind. The rate at which its coma expanded, the speed of ion flow, the alignment of its induced magnetic field, all synchronized with the oscillations of the incoming plasma. When two systems resonate, they exchange energy efficiently, but without chaos. Each fluctuation in the solar wind would have been met by an equal and opposite adjustment in the coma's structure, leaving the nucleus in a state of perfect neutrality. The storm passed, but the dance continued. In laboratory experiments with plasma spheres and magnetic fields, similar phenomena have been observed. When the field lines of an incoming flow encounter a conductive region, they can reconnect in stable configurations that minimize net force. The system essentially reorganizes itself to maintain balance. What we see in 3I Atlas may be this same principle, played out on a cosmic scale. Its coma, charged and responsive, could have acted as a self-correcting field, redistributing stress across millions of kilometers while protecting the core from any measurable acceleration. The most convincing evidence for this lies in the symmetry of the ion tail. Throughout the period of solar activity, even during the CME passages, the tail remained astonishingly straight. A bent or fragmented tail would have implied localized field imbalances, but none were observed. This uniformity suggests that the induced magnetic field within the coma was both coherent and adaptive. In essence, 3I Atlas maintained its own miniature magnetosphere, regulating itself like a planet, but on a much smaller scale. And this brings us to one of the most fascinating parallels in all of heliophysics, the resemblance between cometary plasma environments and planetary magnetospheres. Both have bow shocks, magnetosheaths, and regions of reconnection. Both deflect solar wind through electromagnetic tension rather than direct impact. The difference is only in scale and permanence. Planets hold their fields through metallic cores and steady currents. Comets do it through motion and ionization. One is structural, the other emergent, yet both obey the same laws. In that sense, 3I Atlas behaved like a temporary planet, a transient world whose atmosphere was made not of air, but of electric potential. It's almost poetic to think that an object from another star, moving freely through the solar system, could momentarily carry within it the same principles that protect Earth from the sun's fury. For a brief time, it had its own shield, its own balance between pressure and field, its own electromagnetic identity. And that shield, invisible though it was, might explain why the comet remained so perfectly undisturbed. Still, there are details we cannot ignore. The structure of such magnetic shielding depends heavily on ion density and flow rate parameters we can only estimate for 3I Atlas. If its coma was particularly rich in carbon monoxide or ionized carbon, both highly conductive in plasma form, then the induced magnetic fields would have been stronger. The comet's interstellar origin might also mean it carried different proportions of elements compared to local comets, altering how efficiently it interacted with the solar wind. Chemistry and physics intertwine here, the atomic fingerprints of another sun shaping the electromagnetic resilience of a wanderer. From this layer of understanding, from the certainty of induced currents and plasma shielding, a new line of questioning begins. If such electromagnetic interactions are capable of balancing forces so perfectly, could they also feed energy back into the solar environment? Could the presence of an active coma perturb the local magnetic field enough to seed reconnection elsewhere, perhaps even influencing the behavior of nearby plasma regions? It is not an idle question. Spacecraft have recorded small, transient magnetic fluctuations in the vicinity of comets that seem to originate from their own activity. These perturbations are localized, brief, and weak, but real. If scaled up under the right conditions, they might serve as triggers for larger reorganizations of magnetic structure, like the snapping of invisible cords across the sun's extended field. This line of thought carries us beyond the safe territory of what we know, into the realm of speculation grounded in evidence. To follow it means to ask whether 3I Atlas rather than merely enduring the sun's storms, might have participated in them not as a victim, but as a catalyst. Could its magnetic and plasma environment have interacted with the coronal field itself, shaping the very storms that later swept past it? Could an interstellar object, fleeting and small, influence the star at the heart of our system, if only for a moment? To approach those questions requires both caution and imagination. It means tracing the flow of energy backward, from the comet's electromagnetic shield to the sun's corona, from the certainty of plasma interaction to the possibility of feedback. And that, I suppose, is where the next step of our journey must lead into the hypothesis that lies beyond the measured and into the beautifully uncertain realm of connection, where the visitor and the star might not merely coexist, but converse. It is one thing to describe what has been measured, the certainty of induced currents, the shielding of the coma, the balance of forces, and quite another to step into the space between known facts and possible truths. Here, in that narrow gap, the mind of science becomes both cautious and daring. Cautious, because every leap must be tethered to evidence. Daring, because progress is made only when someone imagines what might lie just beyond the data. And so, in the case of 3I Atlas, one hypothesis begins to emerge, delicate yet provocative. Perhaps, in passing through the solar environment, the comet did not simply endure the sun's magnetic storms, perhaps it participated in them. This is what some researchers quietly began to call the short-circuit hypothesis. The idea is not mystical. It is rooted in plasma physics and the way magnetic fields interact when they are stretched, twisted, or reconnected. In the sun's corona, magnetic loops rise and collapse constantly, storing and releasing energy in flashes of light and heat. These reconnection events are what power solar flares and coronal mass ejections. They are the sparks of a magnetized universe. If, for even a moment, an external object were to alter the local magnetic field lines, to nudge them into new alignments or induce currents that disturb their balance, it could, in principle, trigger or shape such events. Now imagine 3I Atlas as it moves through the heliosphere, its coma expanding, its magnetic field forming a soft cocoon around it. As it enters regions of differing solar polarity, the boundaries of that cocoon twist and fluctuate. Within the plasma sheath that surrounds the nucleus, induced currents flow in complex loops, mirroring the solar field while also resisting it. These currents, by their very existence, produce their own magnetic fields, which in turn interact with the larger ones, extending from the sunday. It is here, in this subtle coupling, that the possibility arises. The comet's field might not only respond to the sun but might also influence it. In this scenario, the presence of a conductive, ionized body like 3I Atlas could locally enhance magnetic stress in the solar wind. As the plasma flows around it, field lines might stretch and tangle. The build-up of tension could lead to reconnection, a sudden release of stored energy that manifests as a CME. The comet, in this view, becomes a kind of catalyst, a seed of instability that triggers a much larger reaction. It is a small disturbance in a vast, already unstable system. Like a pebble dropped into a calm pond, it does not create energy, but it provides the symmetry-breaking moment that decides where and when the energy is released. This idea is difficult to test directly, but the timing is curious. The 3 CMEs that struck 3I Atlas were all launched from solar regions, facing approximately its trajectory. Their directions, though not identical, align broadly with the comet's orbital plane. Correlation does not prove causation, of course, but it invites investigation. Was this alignment a coincidence? Or could the electromagnetic field of the passing comet have contributed to the conditions that led to those eruptions? If this hypothesis has any merit, it offers an elegant explanation for 2 otherwise puzzling facts. First, why the CMEs appeared in such rapid succession, and second, why their effects on the comet's motion were so perfectly neutralized. If 3I Atlas did indeed disturb the magnetic field in a way that triggered or shaped those solar outbursts, then it would also have been wrapped in the very structure it helped create. Its coma would have been a part of the CME's formation process, aligned with its field lines from the start. The storm, in other words, would not have struck the comet as an external blow. It would have grown around it. In that case, the balance of forces we observed would make perfect sense. The CME's momentum and magnetic tension, distributed symmetrically through the coma, would produce no net push on the nucleus. The energy transfer would be internalized, absorbed by the plasma, re-emitted as light and motion, but leaving the solid heart untouched. What looks like resilience would then be something deeper, not the comet resisting the sun, but the comet cooperating with it, moving in synchrony with the very field that appeared to threaten it. Of course, such a hypothesis must meet the standards of disciplined science. It cannot rest on poetic symmetry or observational coincidence alone. For it to hold weight, it would need measurable, falsifiable consequences. Scientists have outlined several. If 3I Atlas truly acted as an electromagnetic catalyst, the solar wind near its path should have shown distinctive signatures, localized perturbations in magnetic field orientation, brief surges in plasma density, or changes in ion velocity distribution. These effects would propagate outward from the region of interaction, forming faint, structured waves in the solar wind, detectable by instruments like those on the Parker Solar Probe or Stereo. Moreover, if reconnection was involved, one might expect transient shifts in polarization in the comet's ion tail, subtle changes in the way light scattered by the plasma was polarized. This could happen as the tail's magnetic field realigned with the new, post-reconnection geometry. Such shifts, if recorded in spectropolarimetric data, would be clear evidence of a coupling event. As of now, the available observations are too sparse to confirm or deny this, but the next generation of solar observatories may be able to test it. Then there is the question of timing. If a comet's passage can perturb the sun's corona, even slightly, we would expect a measurable delay between its approach to a magnetically active region and the subsequent CME. That delay should match the propagation time for magnetic stress to build and release hours or days, depending on local conditions. Some researchers have already begun cross-correlating known comet passages with CME records, searching for statistical patterns. So far, the results are inconclusive but intriguing. There appear to be more CME events coinciding with the perihelion, passages of active comets than random distribution would predict. Whether that reflects real causation or mere observational bias remains an open question. Still, the conceptual framework is solid enough to warrant curiosity. The physics of magnetic reconnection is well established. What is new here is only the suggestion that a passing body might serve as a temporary node in that process. In magnetohydrodynamic simulations, such nodes do appear spontaneously when plasma flows around conductive obstacles. Field lines bend, currents form, reconnection occurs. Scaling those models up to cometary dimensions, especially for an interstellar object moving at tens of kilometers per second, suggests that such effects could indeed reach the threshold of triggering larger eruptions. And yet, there is beauty in restraint. The proponents of the short-circuit hypothesis are careful to emphasize that it does not replace the standard solar models, it merely adds nuance. The sun, vast and complex, does not need comets to erupt. It erupts all the time, in rhythms of its own. But within that rhythm, an external perturbation could act like a conductor's gesture, not creating the symphony, but guiding a single note within it. 3I Atlas, in that sense, might have been one of those gestures, a fleeting influence upon a far greater composition. Skeptics point out that the scale difference is enormous. The magnetic energy of a CME exceeds that of a comet's induced field by many orders of magnitude. How, they ask, could something so small alter something so vast? The answer may lie not in power, but in topology. Magnetic systems, like dominoes, are sensitive to structure. A small realignment in one region can cascade into a larger reconfiguration elsewhere. If the comet's field happened to intersect a pre-stressed region of the sun's extended magnetic network, it could in principle provide the perturbation needed to start a chain reaction. It's not the force that matters, but the timing and geometry. And timing, as we've seen, was impeccable. The CMEs occurred just as 3I Atlas reached critical distances within the solar wind, and their directions roughly followed its projected path. Coincidence, perhaps. But coincidence, in science, is often the first whisper of connection. There is, of course, another, more philosophical implication hiding behind the equations. If this coupling is real, if the magnetic breath of the Sun can be stirred by the passage of a single interstellar visitor, then it suggests that no system, however vast, is entirely closed. The Sun, usually the center of influence, might itself be susceptible to external nudges. The cosmos, in this view, becomes a network of reciprocity, where even a fragment of ice and dust from another star can, for a brief moment, leave its fingerprint on ours. But hypotheses, no matter how graceful, live and die by verification. The next step, therefore, is not belief, but testing. To evaluate the short-circuit hypothesis properly, scientists will need coordinated observations, simultaneous monitoring of cometary plasma, and solar magnetic activity. That means aligning instruments across disciplines: coronagraphs, magnetometers, spectropolarimeters, and numerical simulations working in concert. The challenge is immense, but the reward could be profound: a deeper understanding of how stellar magnetism interacts with the transient visitors that drift through its reach. And so the story of 3I Atlas, for all its wonder, leads us naturally to a broader question. How do we tell apart the extraordinary from the exceptional? How do we distinguish a one-time cosmic coincidence from a universal principle waiting to be discovered? The answer lies, as it always does in science, in comparison. To know whether 3I Atlas is unique or part of a pattern, we must place it beside the other travelers that have crossed our system from beyond the other messengers of interstellar, a space that have come and gone, each leaving behind a different trace of their passage. And perhaps, as we turn to those predecessors to the slender, tumbling mystery of Oumuamua and the luminous, dusty trail of 2I Borisov, we will find context for 3I Atlas's strange composure, and glimpse, for the first time, the true diversity of visitors from the stars.